Welcome to the lecture series on mathematical modeling, analysis and applications. In the last lecture series, we have just discussed all these linear discrete models based on first order and second order difference equations, considering different examples. Then we have just discussed the stability analysis and how to find the eigenvalues and its behavior, considering several examples and several methods. And in this lecture, we will start about discrete time nonlinear models in population dynamics. So, in the nonlinear models, first we will just consider the cell division model here, and then we will just go for like co-wave graphs for nonlinear cell models. Then we will just go for like nonlinear stability analysis, and finally we will just go for like logistic growth function. So, if you just go for nonlinear cell division model here, that in the last lecture for linear difference equations, we have considered like a cell division model also there, and there we have just studied about the analytical and graphical solution of linear models based on the cell divisions. And mathematically, if there are no migration, they have just represented as Cn plus 1 equals to alpha Cn. And already I have discussed several times that if the migration will come to the picture, this cell division model will give you a nonlinear model. The meaning associated with this basic model is that each cell will survive till the end, but does it happen in actually? No. Since sometimes the cells are dying due to like unequal distribution of food or deficiency of food, or there is a competition between the cells. To survive each cell, they need to fight for resources. So, there is a need to include the survival rate, how much percentage of cells are finally existing after certain period. Again, on which factors should the survival function depends on, that we have to consider when we are just going for a mathematical model, and what should be the nature of this function. So, especially we have to consider like the survival function depending on the factors, and what should be the nature of this function. And if we want to find the answer of these questions, how this function is behaving or how this function should dependent on each other, then let us model out the cell division process with the survival function SC suppose. So, since the earlier model, if you just see, it is just written as Cn plus 1 equals to alpha Cn, directly proportional to the cells there. And for this case, we have to consider like a survival function, it should come to the picture. So, that is why we can just consider the total number of cell at time level n, which can be represented as the proportionality constant alpha, then Cn minus 1, whatever the cells are existing n minus 1 time level, and how this surviving cells factors are affecting this transfer of the total number of cells to the nth level. Now, let us analyze the survival function SC. No competition. So, we will have like sufficient food for all the cells. So, each cell can find the food, and there will be no dying of the cells. So, that is why in that situation we can just consider SC equals to 1, and we can just assume Cn equals to alpha Cn minus 1, that is the natural model or the linear model, whatever we have just get for all C. Second case is a contest competition. Here there are finite number of resources. Suppose we will have like 100 cells are present, but the food resource is available suppose for 50 cells. Then first 50 cells, they will just come and they can take the foods. Then we will have a competition for other cells, that they have to like compete this 50 cells to get the food there. So, for that we are just considering that we will have like a resources limitation here, and the cells which are able to take one resource will survive and take part in the next generation. So, we can just consider SC equals to 1. So, first phase, that 50 cells will come and take their food, they will just survive. So, we will have like a critical parameter. So, up to 50 cells we can just define that they can find the proper food without any competition, and we will have then this critical point will exist 50, and they after that the cells will not find any food and they will compete with this 50 cells again. So, that is why that depends on like C critical value with the total number of cells who have got the food, they will just try to find the survival there. So, that is why we are just writing SC equals to 1 for C is less or equal to C critical. Up to 50 cells they can find the food and easily they will survive. For that the survival condition is 1, we are just no competition, it is there. But if suppose C greater than C critical, this means that after 50 food resources, so then we have to consider like C critical 50 cells whoever got the food division over the total number of cells. Third condition is that scramble competition. Here each individual is assumed to share equal amount of limited resources, and if this quantity is sufficient they will survive, otherwise not. This means that, so whatever this resource it is available, it will be equally distributed with all these cells, and if this quantity is not sufficient then one cell will fight with other to survive over there. So, finally, if they will have no food then they will die out there. Hence, we can just consider SC equals to 1 for C less or equal to C critical, the same condition whatever it has been assumed for the earlier case. But in that case, the after this like 50 resources of food, so all other cells they are fighting with the cells to get the food and to survive, but here there is no option, they will just directly die it out there. So, that is why for C greater than C critical the cells will die there. So, then we will just go for nonlinear cell division model. Practically it is not possible for critical value to be fixed, since the cells will come and they will just take the foods. So, we cannot put any barriers or restrictions how they are just consuming the food or how they are surviving over there. Also, zero survival seems unrealistic, at least for large populations. Then how should the survival function act in that cases? Let us assume that suppose this cell function as C into the survival capacity of the cells, or the survival function of the cells, or the number of cells which is satisfying these survival conditions. Now, the contest competition describes the exact compensation as limit C tends to infinity Fc equals to L here, where L is a constant. Suppose that is a, if we are just taking the limiting condition here, this means a infinite number of cells are present, then finally if we just consider this limiting case, we will have like a constant level, we can just get it over there. This represents the situation of compensating any number of new cells with already extinct cells. Hence, SC can be approximated as, since this is just coming towards L here, so we can just write this is SC equals to L by C here for large C. Now, let us consider in general case for SC is approximated, suppose 1 by C to the power B here. That is couple of factors that will just affect this cell populations. We can just assume a nonlinear model, and that is why we can just assume that SC can be approximated as 1 by C to the power B here. So, when B lies between 0 and 1, it is called undercompensation, resources are less utilized. This means that foods will be sufficiently present there, and when B greater than 1, it is called overcompensation, resources are overutilized. This means that this is consumed by all the cells at a time. So, then if you will just go for nonlinear cell division model, if B is assumed to be 1, then there is a contest competition, which means Fc we are just assuming here, and which is eventually levels out a non-zero level for large population. Hence, the population will be stabilized by avoiding too many newborns. If sufficient number of cells will be present, so certain restrictions or constraints they will find to reproduce again the cells, since due to maybe climatic conditions or maybe due to unavailability of resources of food, or certain constraints means they cannot find the proper space to growth of these population levels. Again, if you will just come back to the model based on this equation 6.2, then Cn can be written as alpha Cn minus 1 and Scn minus 1, which can be expressed as alpha, since this is just a complete function here, Cn minus 1 Scn minus 1, which can be written as Fcn minus 1 for n belongs to n. For exhibition of compensatory behavior, if you will just assume this function f of c is constant here and Sc is approximated as 1. For a small c, assuming very small competition among cells, we can find that the growth must be exponential with growth rate of alpha here. And one can use as a simple function of SC, which is a nonlinear function based on this exponential growth rate of alpha as 1 by 1 plus SC here, where A is any constant. Directly this function is just constructed and it has been verified with this experimental observations for the cell culture techniques. So, this leads to the model equation as, if you will just see in the previous slide. So, Cn is represented as alpha Cn minus 1 S Cn minus 1, and if you will just write all these factors, this model can be written as Cn equals to alpha Cn minus 1 by 1 plus A Cn minus 1, where n belongs to n. If we assume the carrying capacity of environment is E, suppose, and the population reached E will stay there, that is, if Ck equals to E for some E, then Ck plus m equals to E for all m greater or equal to 0 for some k here. And if we will just substitute in model equation of 6.4, this will just lead us to like A equals to alpha minus 1 by E here, and the resulting model is given as Ck equals to alpha Ck minus 1 by 1 plus alpha minus 1 by E Ck minus 1, and this model is known as Beaverton-Holt model. And if you will just go for the further analysis of this model can be written in a generalized form as Ck alpha Ck minus 1 by 1 plus A Ck minus 1 B here. So, just a linearization we have just simplification we have just made it out here. This is also known as a Hassel model depending on B, since it compensates both contest competition for B equals to 1 and scramble competition for B greater than 1. So, then we will just go for a stability of this nonlinear system. There are relatively very few cases where analytical solution of a nonlinear difference equation can be computed directly, especially we can just say that it is very few, or we cannot find also in case of nonlinear equation the analytical solutions. A general nonlinear difference equations, especially it can be represented as xn plus 1 as a function of x1, xn minus 1 up to x1 there, where n belongs to n. Thus, we must have to be satisfied with the nature of the system first, that is the stability analysis we have to justify, or with the computer generated system, that is in numerical computation we have to do to find the solution. In order to study the nature of the system, let us consider a general first order equation, because higher order equations with a n coefficients, suppose this can be converted into a system of first order equations. So, you have to analyze that in the last lecture that I have just done for numerical methods. If you will just follow, then you can just find that a nth order difference equation, it can be transformed by using certain variables to a first order difference equation. So, if you will just go for stability analysis of first order nonlinear difference equations, and then first we will just consider a first order difference equation that is in the form of like xn plus 1 equals to f of xn, suppose, where n belongs to n here. There are a lot of importance of steady state solution, especially in problems of dynamics, where growth, propagation and reproduction takes place. An equilibrium or a steady state, especially that we have just discussed in our earlier lectures, relates to the absence of change in the system. Since when with respect to time there is no change, then we will have a steady state. In context of a difference equation, a steady state solution lambda is defined as xn plus 1 equals to xn equals to lambda. Whenever we will have like a fixed point solution, then we are just saying it is a steady solution there. That is, after that we did not find any change, always we will have the same value at each of the iteration levels, which describes no change from generation n to n plus 1. This implies that lambda equals to f of lambda. Mathematically, this point lambda is referred as fixed point of a function, any function. This function takes the value and its value will not get changed. Quite often solving for fixed point is simpler, easier than solving nonlinear difference equation for general solutions. And if you just go for like the steady state solutions, which is said to be stable if all the neighboring states are attracting to it, and if it is not so, then a steady state is unstable. And if the system is unstable, population may crash or the number of competing group may shift in favor of few one there. Now, let us take any arbitrary point, suppose xn, and we want to study that whether this point move away or move towards the steady state. So, if you just see the cobweb method there, so you can just find that first we are just plotting a graph y equals to x, and if you will have this functional curve like y equals to f of x is existing there for any function. So, first we are just putting this point like x 0, then we will have a functional value here, then we are just putting the perpendicular, then we are just dropping this one, then we are just moving this way. So, again we will just putting this one and we are just moving towards this origin there. The same thing we can just do for graphical sense here also. And next, if you will just assume suppose x n can be written as a lambda plus epsilon n, suppose a error term is existing for the calculation of lambda, then we can just consider the exact solution x n as lambda plus epsilon n. Sometimes it is called the Porter solution, and especially here we can just say that epsilon n is a very small quantity which is termed as perturbation of the steady state. And if you just write x n as lambda plus epsilon n here, then x n plus 1 can be written as lambda plus epsilon n plus 1, and the value of epsilon n plus 1 which can be generalized as x n plus 1 minus lambda, and which can be written as like f of x n minus lambda, since x n plus 1 can be expressed as a function of f of x n for fixed point equation. So, then we can just write this epsilon n plus 1 as a function of lambda plus epsilon n minus lambda there, since it is a fixed point function, and which can be written by Taylor series expansion, since a function is a continuous function as we have assumed, and epsilon n is a very small parameter there. So, we can just expand it as like f of lambda plus lambda df by dx at x equals to lambda. And so, directly if you will just expand this one, so we can just write this one as like f of lambda plus epsilon as f of lambda plus epsilon n f dash lambda plus epsilon n square by factorial 2 f double dash of lambda. In that form we can just write. And if you will just see here that f of lambda it is just written, and this can be written as epsilon n square here. Since higher powers of this f double dash of lambda or higher order terms, it is just involved as epsilon n square here. Since epsilon n is very small, so we can expand function f by Taylor series. And if you just neglect this, so we can just write here also like minus lambda should exist, and higher order terms if you just neglect here, then we can just get f of lambda minus lambda plus lambda df by dx. And since we are just assuming here lambda is f of lambda, so this can be written as lambda df by dx at x equals to lambda. And this equation is in the form of like epsilon n plus 1 equals to a epsilon n here, where n belongs to n, and a is can be written as like df by dx at x equals to lambda. Recall from previous lectures, the system will be stable if a mod a less than 1 and unstable if mod a greater than 1 here. So, next we will just go for stability of Beaverton-Holt model of cell division. Consider the Beaverton-Holt model of cell division process and assume parameter suppose a equals to 1 by p and alpha as k by p, where both k and p are positive. Now, the model will be in the form of like Cn plus 1, this equals to k Cn by p plus Cn. It is the especially the model developed as a nonlinear model here. To calculate the steady state, if you just substitute Cn plus 1 equals to Cn equals to lambda, since fixed points we are just using here, there are two steady states. First, if you just put like lambda equals to 0 and lambda equals to k minus p here. Obviously, if k greater than p, because there is no meaning of negative population. So, population should exist when we are just going for the calculation of this population at different levels. To check the stability, find the differentiation of function on right hand side of population at both steady state points. To find that one, if you just put here, that is Cn plus 1 as a function of Cn here, and then directly we can just write k into lambda by p plus lambda, since Cn equals to lambda here, and f dash of Cn, which can be written as k into p by p plus lambda whole square. Clearly, if you will just see here, so lambda equals to 0 is stable when k less than p, and lambda equals to k minus p is stable when k greater than p. So, if you just go for this like behavior of the stability of Waverton-Holt model of cell division, so we can just verify this result by using this co-wave graphs here. So, first if you just plot here y equals to x is the line there, and the function it is just written as y equals to x by 1 plus x, and first we are just assuming any point here, that is you can just consider as x0 suppose here, then you will have this functional value, that is y0 here, then you are just putting this left moment of this line along this y equals to x, then you can just put again this line on the functional value, then we can just move in that form. So, easily we can just verify that all the vertical and horizontal motions are monotonically decreasing, hence the model is stable. So, directly if you just put here this nature of curve wave model for Hassel model for b equals to 0.5 and 2, you can just observe that this will be like the stability condition is achieved here. So, then we will just go for logistic difference equations. Already we have discussed several discrete time models in population dynamics, and all these model were specific to problem, and we cannot think also of a model which can govern many classes of systems, that is different populations, distinct species, one species at different stage of evolution or developments. This new model can have a variety of meaning depend on the parameters involved in it. Now, let us consider a particular type of first order difference equation. Suppose yn plus 1 equals to yn into r minus dyn here, and if you just see this equation involves two parameters r and d here. So, can you reduce these parameters? Of course, yes, and the method used to reduce these parameters, it is called non-dimensionalization. Why do we need to get rid of these parameters? Since sometimes it is necessary to get rid of these parameters, since we will have like a number of unknown parameters involved in certain equations, and the number of computations are directly proportional to the number of parameters. So, if we are reducing these parameters, then we are reducing the computations too also. So, if you will just go for this reduction of these parameters, for this equation we can just put here xn as a d by r yn, and this leads to the equation as xn plus 1 equals to r xn 1 minus xn. Since if you will just see here our earlier equation, it is written as yn plus 1 as yn into r minus dyn. So, if you will just replace here, that is in terms of yn can be written as like r xn by d here. So, from this equation directly if you will just take r common, and you will have like or directly you can just replace xn in terms of yn, then you can just find directly the xn plus 1 equals to r xn into 1 minus xn, where d is just gone out from this equation, and we are left with only one parameter here r. To find the steady state solution, let us substitute xn plus 1 equals to xn equals to lambda here. There are two steady states, so especially we can just say lambda equals to 0 and lambda equals to 1 minus 1 by r. So, for the steady state or for the like stability condition f of xn, it can be written as, if you will just see, r of xn into 1 minus xn here. So, f dash of xn, which can be written as like r into 1 minus 2 xn. At lambda equals to 0, we can just write f dash of lambda equals to r, and at lambda equals to 1 minus 1 by r, f dash lambda is satisfied as 2 minus r here. And the steady state lambda equals to 0 is stable for absolute value of r when it is considered less than 1, and lambda equals to 1 minus 1 by r is stable for 2 minus r is less than 1, or r lies between 1 and 3. So, if you just go for this observation of logistic difference equations for x0 equals to 0.1, perform 20 iterations for r equals to 2.5, r equals to 3.3, r equals to 3.33 and r equals to 3.9. So, we can just find that for r equals to 2.5, after certain time steps we are just getting a steady state here. There is no change of values. But in case of a 3.3 you can just find a periodic oscillation. After certain values it is just obtaining the same values at each of the oscillations. The same scenario it is just observed for 3.33 also. But 3.9 you can just find a huge oscillation of values, that is nothing but the chaos it has been found. So, that is why we have just written for r equals to 2.5, after certain iterations we are just obtaining this steady state, and for 3.3 periodic oscillations with period 2 it is just observed there, and for 3.33 we are just finding this period oscillations of period 2, but for 3.9 it is coming as chaos. In a graphical sense, if you just see here, it is clearly visualized, since in this level you are just finding there is no change of graph here, but here you can just find that the oscillation level is always same here for these two cases. But in this case if you just find there is an unequal change at each of these levels here. So, that is why this graph is especially called your cowish situation. So, in this lecture we have discussed like different nonlinear cell division models, then formulation based on survival rate function, and nonlinear stability analysis, and logistic growth difference equations. So, then we have just studied the observation of logistic growth function with a set of parameter values, then the steady state and transient behavior of the system we have just studied. Thank you for listening this lecture.